Hello! Today I am presenting our work, PhysGen, Physically Grounded 3D Shape Generation for Industrial Design. Existing 3D generative models excel in creating apparently realistic objects. However, such realism is often only skin-deep. If we look closely, as shown in the zoom-in view, the geometry often contains significant inconsistencies or implausibilities. More critically, look at the aerodynamic analysis at the bottom. The standard generated shape results in a turbulent wake and poor performance. In contrast, a shape generated with physical grounding demonstrates much more stable airflow. While visual approximations might be acceptable for entertainment, ignoring these physical requirements is detrimental when the end goal is engineering-oriented design. To address this, we present PhysGen, a physics-guided flow-matching model. Our approach is built upon an alternating update algorithm that switches between two key steps. First, a velocity-based update. In this step, we generate the geometry. Crucially, we incorporate a physics-aware regularization term right here. We update the latent code using gradients derived from the discrepancy between the predicted and target physical values. Second, a physics-based refinement. We then switch to a distinct refinement step. In this step, we calculate physical properties, such as drag, lift, and lateral force. We then use the gradients derived from the discrepancy between the predicted and target physical values to guide the latent code. This ensures the generated shape evolves to meet specific physical constraints. By alternating between these steps, we ensure the generated shape evolves to meet specific physical constraints, like drag or lift, while maintaining high geometric quality. A major challenge for this method is that standard VAES typically encode only shape, making physical properties unrecoverable from the latent space. To solve this problem, we propose the Shape and Physics Variational Autoencoder, SPVAE. Unlike traditional models, SPVAE embeds both 3D shape features and physical information into a unified latent space. As shown on the right, this allows us to decode not just the 3D mesh, but also corresponding physical attributes like surface pressure and drag coefficients simultaneously. Let's look at how this improves generation accuracy. Starting from an input sketch, the generation without physical guidance, shown here in gray, deviates significantly from the ground truth in red, especially at the rear and roof. In contrast, with our physical guidance, the generated blue shape aligns much more closely with the target geometry. As the table confirms, physical cues effectively correct the shape, leading to higher accuracy. This is even more obvious from the front view, where the blue shape is clearly closer to the red ground truth. In real image experiments, we further show that physical information resolves depth ambiguity in single-view 3D reconstruction. From a real single-view image, two shapes are generated without physical guidance from this image, but with different initial noises. As shown in the red and orange cars, they share similar side silhouettes, but diverge significantly in front-view width due to inherent depth ambiguity. When our physics-guided generation is applied, enforcing an approximate target drag coefficient and directional aerodynamic constraints, the resulting shapes, blue and green, converge to consistent and physically plausible geometries. Quantitative comparisons show substantial improvements, demonstrating that incorporating physical information effectively stabilizes 3D shape prediction from ambiguous visual cues. Finally, we apply PhysGen to minimize drag. Observe how the car body and the pressure map evolves during the process. We successfully reduced the drag coefficient. Thank you.